In Chapter 3, we will study two particular methods of analysis of linear resistor network-based circuits. And we will apply Ohm's Law and Kirchoff's current law through these two techniques. One is known as Nodal Analysis, which will be the focus of this video, and then another video will focus on mesh analysis. Nodal analysis is the application of Kirchoff's current law at each node in the circuit. Mesh analysis will be an application of Kirchoff's voltage law around each mesh within the circuit. And no matter what you have in your circuit, whether they're current sources, voltage sources, resistors, we can use these two techniques. In some cases, one of these techniques may be requiring fewer equations than others. It's just one of those things that happens through observation, looking at the nature of the circuits that we are trying to solve for. It depends upon what you're actually looking for in terms of quantities. Using Kirchoff's current law to do nodal analysis will give us voltages, which can convert into currents, and if we do mesh analysis, that will give us currents, which we can convert into voltages. This will allow us to solve several sets of simultaneous equations, and we can use Cramer's rule or the various techniques that you should hopefully have learned in a linear algebra class, including the use of MATLAB or similar computational tools to solve those equations. So, what is nodal analysis? This allows us to look at each node in the circuit and to analyze the currents flowing in and the currents flowing out of those nodes. And so what we're going to do is look at how much voltage changes from one side of a resistor to the other, and then we'll look at how much resistance is in that pathway, and from there we will be able to determine the current through that particular branch. And we will do this at all nodes except for one. We will designate one as our reference node, and that will be considered our 0-volt potential reference, typically referred to as our ground node. We may not have a designated ground connection, but that will be where all of our voltages will be relative to one reference. And so from that we will get n equations to solve for n unknowns, and you can use that the techniques that you have already learned in other courses for solving those equations. So what are the steps? First, we need to choose what our reference node will be. Typically, in most of the problems that we're going to do in this course, they will end up being the node that is at the bottom of the schematic diagram, but not necessarily. And then we will assign voltage names to the other non-reference nodes. And so we will have voltage V1, V2, etc. all the way until we get to the n- first node, which will be the last non-reference node. And at each of the non-reference nodes, what we're going to do is apply Kirchoff's current law. And so we're going to look at all the currents flowing in and all of the currents flowing out of those particular nodes. And of course, we know from Kirchoff's current law, all of those currents need to sum to 0 at each node. And so we will ensure that that is the case, and that will give us our simultaneous equations that we can solve. So let's look at an example. The simplest type of circuit that we can use nodal analysis on involves only current sources. We don't have to worry about voltages. So in this case, we've got two current sources, independent current sources, I1 and I2, and then we've got three resistors in here. And so we don't have any voltage sources. We're going to start by selecting a ground reference, and we're going to select this bottom node. Notice this, and this are all at the same potential. They're only connected by a wire. So this at the bottom will be our ground reference. So we'll just go ahead and add a ground and define that as our 0-volt position in the circuit. Then what we're going to do is assign V1 and V2 to the remaining nodes. And so here V1 will be the potential change across resistor R1, and V2 will be the potential change across resistor R3. So this node will be designated as V1, which is V1 volts above this 0 threshold, and this will be designated as V2, which will be V2 volts above the 0 ground. And so then what we're going to do is apply Kirchoff's current law at each of these two non-reference nodes. And so if we look at node 1 here, this is our V1, what do we have? Well, we can go ahead and decide on the directions of currents that aren't already labeled. It turns out if we're wrong in our guesses for these currents, all we're going to get is something that is negative. So we're going to go ahead and choose directions for those currents, and the math will work out regardless of whether that direction is right or not. And so in this case, what do we have? At V1, the only current that is flowing in is this I1, and then the currents that are flowing out are I2, and then this current I2 and this current I1. And so all of the current flowing in comes from I1, all of the current flowing out are going through these three branches, so those three branch currents sum to the I1 current. Then if we go over here at the V2 node, because we chose this current to be leaving here, now this current is entering V2 over there. We have to be consistent in our direction through this branch. We couldn't say, well, I2 is coming out this way and then over here point it back the other way. So we have this I2 is entering, lowercase I2, which is this branch current through resistor R2. Capital I2 is also entering, which is the current from this current source. And then leaving, we have I3, which is the branch current flowing through resistor R3. Now, what we're going to do is assume that I1 and I2 would be known constant currents. And then what we're going to do is use some algebra and use Ohm's Law to determine our currents I1, I2, and I3 in terms of those node voltages and the resistances here. And so we're going to keep in mind that current likes to flow from high potential to low potential. So what does that mean? We're making the assumption that V1 has a potential that is greater than 0 because current is flowing from this high potential down to the low potential of ground. We're also assuming that V1 has a higher potential than V2 because we're assuming this branch current is flowing from V1 to V2. So our assumption is that V1 has a higher potential than V2. That may or may not be the case. If it turns out that V2 ends up being a higher voltage than V1, all that means is that we chose the wrong direction for this arrow here. It's also possible that potential could be negative, and so it's entirely possible that V1 and or V2 could be at a potential that is less than 0, because remember, this designation of this ground is really just an arbitrary 0 reference. All that means is this may be at a higher potential than either V1 or V2 or possibly both. And so if that's the case, then that would mean that either I1 or I3 may have been designated in the wrong direction, and that's perfectly fine. So these are just arbitrary current directions that we are picking from the offset to allow us to apply some of the Ohm's Law math that we're going to see in just a little bit. So now what we're going to do is look at I1. The current flowing through I1, let's go back. The current flowing through I1 is going to equal V1 minus 0 divided by R1. So that's the potential across R1 divided by the resistance. That's what Ohm's Law tells us. I2 is going to be V1 minus V2 over R2, and then I3 is going to be V2 minus 0 over R3. And so if we plug those back in to the equations that we just developed right here in the previous slide, now what we get is I1 is equal to I2 plus V1 over R1 plus V1 minus V2 over R2, and then we get I2 plus V1 minus V2 over R2 equals V2 over R3. Now we're typically in problems like this going to know what those resistances are. We're going to know what those fixed currents are. And so the only unknown that we would have in a problem like this would be our node voltages V1 and V2. So in this case we would have two equations developed to solve for two unknowns. And so the last step is to solve that system of equations for those unknown voltages. And so that will typically be what we're asked to solve for in a nodal analysis type problem, is what are the voltages, what are the potentials at those different nodes in the circuit. If we were asked to find a particular current, we could go back and then solve these equations. Once we solve for V1 and or V2, we could go back and plug that in to find I1, I2, I3, the various currents through each of the branches in the circuit. Now, what happens if you have things other than current sources? If you have voltage sources, well, there's really two different things that could happen. The simplest case is if you have a voltage source between the reference node and one of your non-reference nodes. Effectively, that establishes a constant. So in this case, we have this 10-volt voltage source, and it has one job. That is to make the difference in potential between where the negative terminal is and where the positive terminal is 10 volts. And so if this is our ground reference, our 0-volt potential, that tells us that V2 is automatically 10 volts. We don't need any other equation. We just look at that and say, okay, by definition, this 10-volt source is making V1 equal to 10 volts. So that is the simplest equation that we'll have. It's just V1 equals 10 volts. You don't have to do Kirchoff's current law to solve for that. Now the other case is when you have a voltage source between two of the non-reference nodes. And so in this case, we don't really know what the current is that is flowing through that voltage source. That voltage source is going to get us as much current as is required to balance out Kirchoff's current law at each of those nodes, but we don't know what that is, and we don't know the internal resistance of that voltage source, so we can't really just use Ohm's law as we have previously. And so in this case, what this will do is allow us to create what is known as a supernode. And what a supernode does is it lumps together two different nodes. So in this case, we're going to create a supernode surrounding this particular branch. And we're going to say all of the currents entering that supernode, that would be I1 here, I2 leaving, I4 entering, and I3 leaving, will now sum to 0. And the reason for that is what we would actually have if we just went to the V2 node is we would have the current I1 entering, the current I2 leaving, and then we could pick a direction for the current through this particular voltage source. That could either be entering or it could be leaving, depending upon how we designate that. And we would add that up. And then over here, we would have a very similar equation, I4 entering, I3 leaving, and then the current through this voltage source either entering or leaving. Effectively, what we're doing with the supernode is we're forming those two equations and then just bringing them together as one big equation. And since that wouldn't yield, if we just lump those together, that wouldn't yield n equations. That would actually give us n minus 1 equations to solve for n unknowns. We need an extra equation. And that extra equation is going to be a constraint equation, which will tell us that V3 plus 5 volts is equal to V2. And that's just going back to the definition of what is this voltage source doing for us. It's raising the potential from V3 to V3 plus 5 at V2. So you would add an equation V2 equals V3 plus 5 volts if you had this particular circuit to solve. So a supernode, to summarize, allows us to enclose a voltage source, and it could be dependent or independent, between two non-reference nodes, and allows us to still do nodal analysis even though we don't necessarily know what the current is through that particular source. Alright, so in this example, let's go back to our equations. our current balance would still be at the supernode I1 plus I4. Those are the two currents that are entering, I1 here and I4 there, equals the two currents that are leaving, that sum. So I2 plus I3 are leaving. And then we can express those in terms of their differences in potential. So I1 is V1 minus V2 over 2 ohms, and then we have V1 minus V3 over 4 is this I4 current, and then we have over here V2 minus 0 over 8, that's our I2 current, and V3 minus 0 over 6 is our I3. And so we can look at both sides of those equations, and in this case we have 4 unknown currents. We also happen to know V1 is equal to 10 volts, so that becomes a constant. And we also know that V3 plus V2 happens to, V3 plus 5 volts happens to equal V2. So that's the other equation that we can develop. So if we were to analyze this, we can think about going around this particular loop, and we would see minus V2 plus 5 volts plus V3 happens to equal 0. And so that is just applying Kirchoff's voltage law around that bottom right mesh. And so that allows us to develop this particular equation, V2 minus V3 is equal to 5. And so the properties here of the supernode, the voltage source inside the supernode provides this constraint equation. And so that's typically what I refer to as, okay, what is the constraint when you have the supernode? Because now you're going to be lumping together two normal equations into one. That requires us to have this extra constraint equation, so we still have n equations for n unknowns. And so a supernode really requires an application of both Kirchoff's current law and Kirchoff's voltage law, because we're trying to balance the voltages that are happening around any particular mesh in the circuit. So this concludes our introduction to nodal analysis here, and I will post another video that has an example of how to use nodal analysis for problem solving. Next video, we will get into mesh analysis.